Okay, we're particularly interested in the number density on these upper and lower surfaces of the part of the system that the beam passes through for most of its trajectory. So we're going to add an average operator that we can use in post-processing to compute averages over these two surfaces. So I can right-click on the definitions node, choose model couplings, and click average, and then I want to change this to be a boundary selection and choose these top surfaces. I like a second average operator which I can use to compute averages on the bottom surface here. Okay, great. Now what we'd like to do is solve the problem with a range of different values of theta so that we tilt our wafer within the vacuum chamber, and that's very straightforward to do. We just simply add a parametric sweep to our study. So I right click on the study node, choose parametric sweep, sweep over the parameter theta, although I could add any of the parameters we've chosen, and indeed you could combine a sweep over theta with a sweep over the pump speed. In this case I don't really want to do that, but I'll just sweep over theta. I can type in a list of values here, or I can set up a range using this button. I'm going to start in this case at 0, go up in steps of 20 degrees to 60 degrees. And now all I need to do is to right click on the study 1 node and choose compute to solve my problem. By default in Comsol we're going to get 3 plots without doing anything. So we'll get the incident molecular flux, the pressure, and the number density plotted on the surface of the chamber. You can see that although we can see all the exterior surfaces, we might want to see some of the interior surfaces in the model, and so what we can do to do that is go into the datasets section here, choose solution 2, which is our parametric solution, right click on it and choose duplicate. Then what we can do is add a selection to that duplicate solution, and if we change the selection to be a boundary selection, start with all boundaries, but then we can manually remove some of these boundaries just so we can get a look inside the chamber. Let's get a good look in there, like that. So now if we want to view the sort of cut-out solution, we just switch to solution 3 and we can see right inside the chamber. Similarly, we can do the same for the pressure, plot that, and the number density. Perhaps we don't like using the units of Pascal for pressure. It's really easy to change those units. We just go in here. Let's say we prefer torr. You can see the range of units that are available by default in Comsol, but let's go with torr, and we can see we're getting about 0.2 millitorr of pressure on the wafer surface, which is the maximum pressure in the system. And we can see right inside our system like this. Now we were particularly interested in the number density, and in particular on these top and bottom surfaces. One thing we could do is perhaps for a particular angle look at how the number density varies along this midline, the center line shown here, and we can do that by right clicking on the results and adding a 1D plot group. We want to use solution 2 in this case, and we'll just use the 0 angle, but we could always change that later if we were interested in all the angles. I want to add a line graph in this case because I want to plot the number density along a line, and I can select in the geometry the line along which I want to plot the number density. Then I need to choose to plot not the incident molecular flux, but the number density. And we can see a plot along that arc of the number density. Let's say I wanted to look at the lower surface. That's also pretty straightforward. I just duplicate this line graph, clear that selection, choose the lower line. Now in this particular case, Kامsól has a sense for its arc length, and we're going to see that the sense along this arc is opposite in direction to that along the top arc. So the plot looks like this, but it's really easy to change that. We can just change, instead of plotting the arc length, we just use an expression. We can see that the arc length goes from 0 to 1.25. Kامsól has a built-in parameter for the arc length, so we just do 1.25 minus this arc length parameter, plot, and we see we've reversed the direction that S is defined in, or S1 is defined in. So we can see the number density is pretty similar on the upper and lower surfaces, and it changes fairly significantly along the course of that beam line. Now we can use the average operator that we defined at the beginning just to look at the average number density on the upper and lower surfaces. So again, we can do another 1D plot group. In this case, we want to do a global plot, and we want to use the average operator that we defined previously, which was called avop1. We want to operate on the number density n, and this one gave us the upper surface. We'd also like to see the lower surface, so we can use avop2 that we also defined, and then I'm going to label that as the lower surface. So we can plot that. If we go back up here and choose solution 2, we want to plot that over all parameters. Click plot, and we can see now how the average number density in the region of the beam path changes as we change the angle theta of the wafer normal with respect to the beam line. So we can also add labels. Perhaps we want to put theta in. For the lower surface, and the upper surface we can put average number density. For the y-axis, sorry. And again, within here you can type in Greek letters, you can use special symbols and so on and so forth, subscripts. So you can really make nice plots. Okay.